Good afternoon, everyone. This is Mrinalini, and welcome all of you for this 12th and I think last interactive session for this NPTEL course, Experimental Physics 2. Course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I'm PMRF Research Scholar Mrinalini, and teaching assistant for this course interactive sessions. So this is the 12th interactive session. I think we may get extra session on 16th where we can discuss some more questions, and if you guys have some doubt also we can discuss how the exam will be online, so a little bit information regarding that. Okay, let's start today's session. First we'll have quick recap of last week's things that we had discussed. So last week we had discussed about is polarization of light, what is unpolarized light, what is polarized light, how we get polarized light. Then we had discussed what is sigma polarized light, what is pi polarized light. Just let me just see. So with this polarization, this we had discussed, and then so we had discussed what happens is, just to quick recap, when we have unpolarized light, if the light is traveling in this direction, then what happens? It has electric field vectors and magnetic field vectors, right? And they are both perpendicular to each other and also to the direction of uh, propagation of light itself. So usually the strength of magnetic field is very less, so we only represent or consider electric field vector. So what happens is, electric field vector for unpolarized light, just to recall, for unpolarized light, electric field vector we show if I am seeing from the front. This is where the light is moving. If I see from here, I will see that electric field vector component, it will vibrate in all the possible directions with the same magnitude. Then I call it unpolarized. When we do something and the light electric field components variation restricts to one plane, either this plane or this plane or at some angle, but electric field vector starts varying in only that particular direction, then we say that the light is polarized, and usually we call it line polarized or plane polarized, that the polarization is restricted to this particular plane. And if I'm seeing it from the front, means the light is traveling out of the plane right now, okay, in all these cases. So this is called plane polarized. And then we had discussed sigma and pi and circular and elliptical polarized light. So after this, we had seen what are the various methods by which we can polarize the light, like dichroism, scattering, reflection, birefringence. These are various reflection. We had seen a very distinct. Then this was the experiment through which we can find out previous a week we had discussed about extraordinary ray and O ray, right? There are some birefringent material like calcite crystal, through which, I mean, in different direction. In one direction we just get one light outside, but there is some other crystalline direction in calcite crystal, along which the ordinary ray, we get two rays, ordinary ray and extraordinary ray. They have different refractive index in that direction, and their velocity changes and these things. So this was one experiment to find out the refractive index for ordinary and extraordinary rays in this calcite prism. Then we had understood polarimeter, and it tells us how much is the polarization, and this was the experiment based on it. Then we had discussed zone plates, how we make them. They alternate dark and transparent zones through which when light passes, we get depending on which zone we are covering and which is uncovered, we may get large amplitude at the other side, and it acts as a convex lens. So we had understood its theory and it's working. So this was the things we were discussing last time, and now we'll be discussing about, so it's little away. So in this course till now we were mostly covering convex lens, mirrors, so it was all about optics. Now there is something this week the lectures were based on the quantum physics experiments. Like we knew we had classical physics, and then classical physics theory was not able to explain certain experiments like black body radiation, photoelectric effect, and these things. Then this concept of, I mean, in classical physics we used to understand that light is a wave, and depending on it we were trying to explain everything. But when that theory failed, so it also used to think that energy is continuous. But these hypotheses failed to explain black body radiations that we were seeing and photoelectric effect. Then Planck was a scientist who gave this concept that photons, that like energy is can also be considered as wave, I mean packets. That light we consider in classical that is wave, it's continuous. Then it gave birth to quantum physics where we consider energy or light electromagnetic wave is packet of energy, and that packet or that unit or quantum we call as photons in case of light. Like electron, right? We see matter when we see, usually we see it's continuous or something, but at the fundamental level it is made of electron, that unit of charge, and then it builds up the whole atom, and the atom makes up the matter. Similar way we used to think that light is electromagnetic and continuous. That also with that rule also we are able to explain certain things where the discreteness doesn't matter. But when we got to know these kind of black body, photoelectric effect, Compton effect kind of things, then it became important to see that light also has, apart from wave nature, light also has particle nature. And only when we consider the particle nature, we'll be able to explain these black body radiation and photoelectric effect kind of phenomena that we are seeing. And the important consideration here is that light is made up of packet of energy packets of energy, which we call photons. Okay, these packets of energy which we call photons, and based on this we'll see how the photoelectric effect, I mean when we perform this experiment, the observations that were seen, how based on this quantum physics theory it was explained, which we could not do using classical theory. Okay, so based on photoelectric effect experiment, so the experiment that was discussed here was we had to determine Planck's constant. Must be knowing now, we know Planck's constant 6.626 times 10 to the power minus 34 joules second, right? And we have to find out the value of Planck's constant from the stopping potential measured at different wavelengths, and study the effect of incident intensity on photocurrent and stopping potential. I mean, this photoelectric effect experiment contains a lot of parts where we vary the voltage and get different stopping potential. We vary the intensity and see the change in photocurrents. These are the two parts that were discussed. Let's first discuss the theory behind photoelectric experiment. So the background of photoelectric effect comes from, it could only be explained by quantum physics, and where we say energy is quantized, Planck's constant times this frequency of that light. Okay, and it could only this is the energy of one photon. If we talk about n number of photons, then it will be given by this, right? n is number of photons. Planck introduces a new fundamental constant, this h, to explain black body radiation. And based on this, then Einstein gave this concept. Actually, yeah, so Planck gave this quantized thing, and then Einstein had explained photoelectric effect by continuing this notion that yeah, the light is quantized and we have something known as photons, wave packet, and energy of one photon is h nu. Okay, so classical concepts, as we were talking about, it never focused or thought about that wave can also have particle like behavior. So as I said, we were just thinking electromagnetic wave, as we call light as an electromagnetic wave or any other electromagnetic wave, gamma ray, X-ray, whatever, they all behave like waves. They are continuous and they have continuous energy. But we never thought that it may also behave like particle, which was Planck's hypothesis, using which it was successfully almost able to explain the black body radiation. That particle, and there's vice versa also, that particle may also behave like wave. That was given by de Broglie hypothesis, and its effect is prominent when we talk about quantum level. In classical means when the objects or particles we see around, their wave will be, actually wavelength will be very small. That's why even if we don't consider their wave nature, it's fine. But at quantum level, this becomes very important. Position and momentum of particle cannot be measured accurately simultaneously. This is Heisenberg uncertainty principle. Okay, that says the uncertainty in position of a particle and uncertainty in its momentum, it cannot be zero. It will always be some uncertainty in the position. If we know certainly the position of the particle, we are talking about quantum level, okay? Because again, what happens in classical level means at the level if you see around yourself, if you have kept some box at some position, you know its position also, and if you're moving it, you know its momentum and where it will reach if you started pushing some box. Say its momentum, you know its mass, you know how much velocity you are giving, then you know its momentum, and then you will know finally where it will reach. So everything is known when we talk about classical regime, like the things around us. But when we start talking about quantum level, about subatomic particles, atomic particles, that time this thing happens that we cannot tell a particle's position and momentum both with certainty. Okay, if we know its position certainly, then we cannot say about its momentum with accuracy, and vice versa. So this is also one another thing that comes into picture when we talk about quantum regime. Another thing is energy of wave is related with frequency and it's quantized. As I said, for one photon energy we say h, Planck's constant, multiplied by frequency, and when we talk about n number of photons, then it's depending on number of photons, energy will be multiple of it. So these were the new concepts that were introduced under quantum physics. Interference and diffraction of light are explained from wave property of light. As you till now, when we were talking on optics about diffraction, about interference, dispersion, we were talking about wave property of light. Light is coming, getting reflected, getting refracted. There we didn't bother about the particle nature of light. We were just considering them, showing them by arrow, by these, because we thought they are wave. The intensity of light are well described by square of amplitude, we know, of the light wave. This we saw in Malus's law also. Intensity is given by amplitude square of the light wave. Intensity of light is nothing but energy of light. The concept of energy of light was unable to explain photoelectric effect. That's what I said. We were considering energy of light is square of amplitude, and that is what is energy of light. But with this, we were unable to explain photoelectric effect. So let's first see what do we mean by photoelectric effect. Okay, so what was observed that when electrons, we had some metal surface, this we saw, and then I'll just first tell what is this thing, and then what were the problem in understanding why it's happening or not happening. So if we have a metallic surface, it has some loosely bound electrons, right? And when some incident light is falling on it, as you can see here, there's a metal surface, they will have some loosely bound electrons. And when the incident light, with some energy of course, falls on it, there are some electrons ejected from the surface. This is what we basically mean by photoelectric effect. It could be any type of metal surface. Metal surface, it's easy to eject electron. Insulator, you know, they are tightly bound, they don't have free electrons. So maybe we won't be able to see because a lot of energy is required there. So photoelectric effect is a phenomenon in which electrons are ejected from the surface of a metal when light is incident on it. By light, we don't mean visible light, by electromagnetic wave. We mean electromagnetic wave. Okay. So when electromagnetic wave is incident on it, these, depending on different material, the requirement of this will be different of the light. That's why we just generally call light or electromagnetic wave. These ejected electrons are called photoelectrons because they were ejected when I'll tell you again, it's because of photons, right? I said light is made up of photons. So because photons were incident, that's why these electrons were ejected. That's why we also call them photoelectrons. But these things, understanding came later. First, what we saw was that when light was some specific kind of light, usually we use monochromatic. Monochromatic light of particular wavelength, when it was incident made to incident on metal surface, there was some electrons ejected. And in experiment, if we put some kind of voltage, then the electrons will flow in direction and we'll be able to get the current. Then we'll get to know, okay, some current is some electrons are getting ejected from metal surface and they are giving us the current. The process through which photoelectrons are ejected from the surface of metal due to action of this light is referred to as photoemission. This process, the photoelectric effect occurs because the electrons at the surface of the metal tend to absorb energy from the incident light and use it to overcome the attractive force that bind them to metallic nuclei. So we know when we have an atom, okay, we have a positive core which has neutrons and positrons. Then there are, Niels Bohr had explained that there are discrete energy levels and energy is momentum is quantized and the electrons are in these energy levels. So they are bound. This is positive charge, this is negative charge. They are bound. They are not going without we supply them some energy to overcome this binding energy. So when this light that I said, it has some particular energy, when that energy is sufficient enough to excite the electrons so that it's able to overcome the binding energy, then only we'll be able to see these emissions. Otherwise, if it's not giving it sufficient energy, then we won't see this photo emission. Okay. So this was what is a photoelectric effect basically about. So history of photoelectric effect, if you talk about, so it was first introduced by Wilhelm Ludwig Franz in the year 1887 and the experimental verification was done by another scientist, Hertz. They observed that when a surface is exposed to electromagnetic radiation, this is what in last slide we were calling light, is exposed to electromagnetic radiation or electromagnetic wave at a higher threshold frequency, radiation gets absorbed by that surface, that metal surface, and the electrons are emitted. Today we study the photoelectric effect as a phenomenon that involves material absorbing electromagnetic radiation. This is our material which absorbs these energies and electrons get sufficient energy to leave the atoms. Thus, this is a phenomenon that involves material absorbing electromagnetic radiation and releasing electrically charged particles. And we know electrically charged particles means we are talking about electrons here. Explaining this, so a photoelectric effect cannot be explained by considering light as wave, because when we consider light as wave, that means it has continuous energy And if there is continuous energy, then we should see at any level of energy, we should see some electrons ejected. And it was also thinking maybe we'll increase the intensity, then we'll get more uh, kinetic energy of these ejected electrons, because we thought intensity means energy of wave. And as we increase the energy, the because see, the electrons will eject after the required, that I said they need some required energy. If they get that, if they don't get that, they will not be ejected, but if they get that, then they will be ejected. And if the energy is more than that requirement, then they will be ejected, plus they will have some kinetic energy. Okay, so we thought if it's continuous and its intensity is amplitude square and it's the energy, then if we increase the intensity of light, that is the energy of light, then kinetic energy should increase. But that was not happening. The intensity, what we observed was that with increasing the intensity of light, number of electrons were increasing, but kinetic energy of electrons was not increasing. Kinetic energy was remaining same. Only number of electrons that were increasing when we were increasing the intensity of light. So this classical physics could not explain this. Also, there were several more things that we'll discuss. So that's why I'm saying that this photoelectric effect could not be explained by this classical theory, which considers light as a wave. However, this phenomenon can be explained by the particle nature of light, in which light can be visualized as stream of particles of electromagnetic energy. These particles of light are called photons, and that's why this phenomenon is called photoemission. The energy held by one photon is related to frequency of the light via Planck's constant. Energy of one photon is related to the frequency of that particular light and multiplied by this Planck's constant factor. Or we know C is mu times lambda, frequency times wavelength. So mu becomes C over lambda. So with frequency or with wavelength, this is the relation of energy for one photon, where E denotes the energy of photon, H is Planck's constant given by Planck, V denotes frequency of light, C is the speed of light in vacuum, lambda is the wavelength of light. Okay. Now, there is some threshold energy required for the photoelectric effect that I was telling you. For the photoelectric effect to occur, it's not like any random wavelight we'll throw and we'll be seeing electrons emitted. There is some minimum requirement of energy so that the electrons can come out of that binding energy, right? The positron is holding them, so they need some minimum energy to come out of break the bind, which is more than which is equal to the requirement of binding energy, so that they can break the bond. I mean break it is equal to their excitation energy, and they can come out of the atom. So for the photoelectric effect to occur, the photons that are incident on the surface of metal must carry sufficient energy to overcome the attractive force that bind the electrons to nuclei of the metals. This is what we are talking about. The photons, that is the light, photons are what? The packet of energy. That is, we are talking about lights, but now we are emphasizing on its particle nature. That's why instead of calling it just light or electromagnetic waves, now we have started calling photons, because we want to emphasize that we are focusing on the particle nature of these incident rays. Okay, so the photons which are incident on the surface of metal must carry sufficient energy to overcome the attractive force that bind the electrons to the nuclei of the metals. The minimum amount of energy required to remove an electron from the metal is called the threshold energy. The minimum amount of energy required to remove an electron from the metal is called threshold energy, denoted by the symbol phi. For a photon to possess energy equal to threshold energy, its frequency must be equal to threshold frequency, which is the minimum frequency of light required for photoelectric effect to occur. As I said, there is minimum requirement of energy. Only when that amount of energy wave is incident, then only the electron will be able to break the this attractive force and come out. So the minimum amount required is called threshold energy, and when the electron comes out, if the energy it got was equal to threshold energy, then it will just come out and its velocity will be 0. But if the energy is more, it will come out also and it will have some kinetic energy also. Okay. So the threshold frequency is usually denoted by symbol this. Usually we write it in subscript threshold frequency, and the associated wavelength will become threshold wavelength. The relationship between threshold energy and threshold frequency is this. So this is the threshold energy, minimum energy required for the electron to come out of the surface of the metal, and a relation between energy and frequency we know. So that's why it becomes like threshold energy depends on threshold frequency. Okay. So again, what happens? This is, say, potassium is a metal, right? It requires 2 electron volt to eject an electron. So if potassium has threshold energy of 2 electron volt, then if I am making incident a red light, okay, whose wavelength is 700 nanometer, its energy is 1.77 electron volt. We can find out from, right, E is equal to hc over lambda. So lambda is 700 nanometer, h is a Planck's constant 6.626 times 10 to the power 34 minus 34 joule second, c is speed of light in vacuum. We can find out the energy of this red light. As you can see, the energy of red light is 1.77 electron volt here, and the threshold energy of potassium metal is 2 electron volt. That means it's not sufficient, so that electrons cannot break the attractive force and come out. So we'll see no ejection. Okay, so doesn't matter how much intensity you will increase of this light. Like you were earlier, say you were using one source of red light, like one source of red light you were using. Now you will think, okay, let me increase the intensity by using 2 sources of red light. So you have increased the intensity that is incident on the surface, but still you will not see the ejections, because intensity we are increasing, but we are not increasing the energy. We are not able to meet the energy requirement, because energy, one red light source or 2 red light source, the energy of those sources will still be 1.77 electron volt, which won't be sufficient, because the first excitation level energy is 2 electron volt. So it doesn't matter we use one red light source or 100 red light sources, we will still not be able to get photo electrons out of this metal. So this is the case with this red light with us this energy. Now if I use this green light, which the energy is 2.25 electron volt, so it's more than this, so we'll get the electron will be able to come out also, and the remaining 0.25 electron volt will be its velocity. That will be maximum. So here for this case we will be able to see photo emission, we will get photo electrons. So for green light, if I increase the intensity by increasing the number of sources, say, or any other way, whichever is possible, but we are increasing number of sources, say, and that's how we are able to increase the intensity. Now when we'll increase the intensity, so we'll be seeing more number of electrons coming out, but their velocity after coming out will be same, because they are using 2 electron volt to come out, and the remaining 0.25 electron volt they are using, they will become their kinetic energy. So even if you use 2-3 sources, it will make more electrons to come out. Intensity you can consider as number of photons that are coming. In a way, for understanding what is happening, you can think intensity is like number of photons. Okay, so more the intensity, more number of photons reaching, but energy of every photon is same. Energy of photon is h nu. So energy of photon is same, only number of photons. Earlier, say one photon was coming, it was knocking off one electron. Now two photons are coming, it will knock out two electrons, and so on and so forth. But the energy of every photon is same, so the electron that is ejected, they all will have, if they are from the surface, if they are from even inside, then they will use some extra energy to reach the surface, and that will be different. But from one place, whatever the electrons is coming out there, this is the maximum velocity they can attain. Okay, if they are coming from the surface. If they are coming from down below, they will use some extra energy to reach the surface, and they will use some extra energy, remaining little energy to come out, which is 2 electron volt, and the remaining value will be their velocity. So velocity, maximum velocity can be this, other velocities can be less even if you increase the intensity, because increasing the intensity, as I said, you can understand it as number of photons. So higher the intensity, more are the photons. So like each photon will interact with one electron, and the number of electrons we'll get will increase, but their velocity will not be able to cross this maximum value. Okay, this is another thing. Now if I use this light of 3.1 electron volt, so its energy is more, so the electron will come out also, and it will get this, its its velocity will be higher than what we saw when we were using this green light. So here, even if the we are just using one source, the electron that is coming out, its velocity will be higher. Why? Because the energy of this photon was higher. So this is the few things we need to understand, how the intensity changes the number of photoelectrons, how the energy influences the photoelectrons and the photoelectric effect. Okay, so the relationship between energy of photon h nu and the kinetic energy of emitted photoelectron can be this: the photon will have the energy, so incident, I mean photon has some energy, some of it will be used by, as that we are calling threshold energy, some of it will be used for the electron to come out or break from the attractive force, and the remaining energy it will use as it will be given to electron as its kinetic energy. So if the photon had energy h nu, then it is equal to the threshold energy, and the remaining will be, this is, this is photon energy, it will be used by threshold, some part of it will be used to overcome the threshold, and the remaining will be manifested as electrons kinetic energy. This is mass of electron and this is velocity of electron. Half mv square will be the kinetic energy. Okay, and so this is what the photoelectric effect more that we discussed. Now, okay, so in the experiment what we were doing, we had some material where we are incidenting some light, which is, now we know it has particle nature, so it's like stream of photons. I'm just doing this for explanation that we are seeing, and we cannot exactly say it's circular ball kind of thing, but it's some sort of packet of energies where each individual photon has energy of h nu depending on which kind of EM wave it is. So these streams of photons are incident on the metal and the electrons are ejected, and through this circuit we are able to detect them. The more the electric current means more electrons are ejected. So this is the basic setup, and then for some particular thing to see, we apply some opposite voltage that we call retarded voltage or retarding voltage, that opposes the flow of electron actually for some specific things that we want to measure. But this is the basic setup of photoelectric effect, that we have a metal on which when light is incident we get photoelectrons, and then we change the light intensity, then see how the current is changing, or when we change the energy of light, then we see how the electrons, photoelectrons and photoelectric current is changing. Okay, so this was all about photoelectric effect, which again was we could not explain it using classical effect, but we were able to explain the things that we were observing using this new concept that light is made up of wave particles. It has particle nature. Okay. So what was observed, as I was saying, electron kinetic energy. So till light frequency means the incident light. The incident light has some energy which is multiple of the frequency. So when it was incident on the surface, until it is more than equal to the threshold energy, we could not get any photoelectron outside. When it reaches the threshold frequency, then we get some electrons. Okay, and as the light energy is more than the threshold energy, then more is the remaining energy goes as kinetic energy of electron. So below threshold energy, no kinetic energy, because the electron itself is not coming out. After, at threshold energy, the electron will just come out, but it will have no kinetic energy. That's why it's zero here. The kinetic energy at this mu naught is zero. And as the frequency of incident light keeps on increasing, the electron ejected have more and more kinetic energy. Okay, so this is what this graph is showing. This is one observation from there. This happens when we change the source energy. We use the source light. We use light source of different energies, means different frequencies, and then we see how the kinetic energy is changing. Then there another graph is light intensity and electron kinetic energy. Light intensity, again what I said, is like number of photons. The more is the photons incident, the more will be number of electrons ejecting, but the kinetic energy will remain same because the photons have same energy. Just by increasing the number, the energy of electrons will not change, because the number of photons, increasing or decreasing number of photons only increases or decreases the number of ejected electrons, but their kinetic energy remains same. So if the light intensity is less than the threshold frequency, then there will be no electrons ejected. That's why we are showing kinetic energy is zero. But when this incident light's frequency is more than threshold frequency, then the kinetic energy is there, but even if you increase the light intensity, means increase the number of incident photons, still the kinetic energy of ejected electrons will remain same. The maximum will remain same. Okay, there is another graph. So light frequency, again the incident light, if its frequency is less than threshold frequency, that means no electrons are ejected. Electrons are not ejected. That's why in this experiment we will see no current, because no conducting electrons. But beyond this threshold frequency, if the light frequency that we are making incident, its frequency is more than threshold frequency, then we will see electric current, and the current will be same if we are not increasing. This light frequency is same, then electric current will same. Only when light intensity we increase, means number of photons incident on the surface will increase, then only number of electrons will increase. Otherwise, if it's like light frequency, if one photon is incident, then one electron will be ejected if it is more than threshold frequency. If it is less, then no, zero electrons will be ejected. But if the light is this mu is more than mu naught. So if 5 photons are coming, 5 electrons will be ejected. So like this. So here we are not increasing the number of photons, we are just changing the light source. So first we use a less frequency light, then more energy, then more energy. So after particular threshold frequency, we will see number of electrons will be same, only their kinetic energy will increase, because if we increase the incident energy source, Then the threshold frequency, after the threshold frequency, everything they is changed to their kinetic energy. So kinetic energy will increase, but number of particles, number of electrons that are rejecting will remain same. So electric current will remain same. Then light intensity versus electric current. Just now this is what I was saying, that number of electrons ejected will be same because number of photons incident are same, but light intensity we are increasing, means number of photons incident on the metal surface is increasing more. So one photon was incident, so one electron was out. Two photons were incident, so two electrons were out. So that's why when we increase the light intensity, that is when we increase number of photons, electric current will increase. This is proportional, linearly proportional. So these are the graphs to get what is happening in theory, this photoelectric effect. Okay, I hope you guys understood everything. If you have doubt, you can ask, and we can. Okay, so this was all about photoelectric effect. I hope this is clear. First, we understood how classical physics was not able to explain when it was just considering wave nature of light. Then comes Planck's hypothesis that light can also have particle nature, using which he explained black body radiation. And taking it further, the scientist Einstein, he gave this photoelectric effect explanation, that each photon is coming giving sufficient energy, more than threshold energy of that particular material, and that energy the electron is taking, it's coming out, and the remaining energy is becoming its kinetic energy, and the other things that are happening around in this experiment. Okay, so I think this is clear, this should be. And then let's move on to Thomson experiment. Let me just check this recording is happening fine. Yeah, okay. So next experiment is Thomson experiment to determine specific charge of electron. So what happened? So in 1808 or this time, they understood matter is made up of atoms or molecules. This they understood. But they were not able to explain further, or I mean say that they just understanding till this time was that matter is made up of some atoms or molecules, and different material means different atoms they are made up of. Then around 1833 period, Faraday's law of electrolysis gave that there is some existence of elementary unit of, there is elementary particle which is made up of all matters, and it has some charge also. Okay, then there was experiment, or this scientist Tony proposed the natural unit of electricity, something like this. In 1897, J.J. Thomson first measured directly the charge of this particle that we started calling electron. So we started with this thing that materials or matters are made up of atoms or molecules, but even atoms are made up of some fundamental unit. This was later proposed, but was first we measured its charge by Thomson, and this experiment is called Thomson experiment, to find out the charge of that particle. Okay, so what we do in this experiment is we have a source. Okay, doesn't matter, some kind of source through which we are able to eject some electrons. Either we are heating or doing something else, or who knows, photoelectric effect that we just now discussed, but some sort of source through which the electrons will be ejected. And then, where is my pen? Okay, yeah. The electrons are ejected from this source, and they go and hit on a screen. This is fluorescent screen. So they will give their charge here. We will see some brightness, and we will see, okay, this is the position where the electron has hit. So now this is very, like, using all the physics, this experiment was designed, and using this we were able to find out the charge of electron, that we now know we represent charge of electron as E, and the value is 1.6 times 10 to the power minus 19 coulomb. So using this experiment he was able to find out specific charge. This was not simply charge, it was specific charge, means the charge of electron per unit mass. So this is what we can find out using this experiment. So what we do in this experiment is, so again we have this source of electrons. Electrons are coming and hitting the screen, and we see the position, if this is the center. Okay, now if we apply electric field, if we apply voltage, the electrons are passing from here and we are applying electric field. Say this is x-axis, so electrons are going along x-axis and the electric field we are applying is along y-axis. Electric field is along y-axis by putting positive and negative voltage difference. Okay, and electric field is given by voltage per unit distance, right? So this is the length, so voltage per unit length will be giving us the electric field which will be experienced by these passing electrons, and the force due to electric field on the electron will be charge of that particle. Right now we are talking about electrons, so charge of that and the electric field impacting on it. So it's linear. The force due to electric field on the electron will be this, and force we know is mass times acceleration. So mass of electron and the acceleration due to this electric field. So electrons are passing like this. We have applied voltage in y direction. Now electrons, if there is zero electric field, then electrons are ejecting in x direction, they will continue to go in this direction. There will be no deviation from this path. But we are applying electric field perpendicular to this direction of its motion, which was x-axis. Now we are applying field in y direction. So it will experience acceleration or force along y direction, and it will start doing this parabolic path. It will start here and then it will start shifting to y direction, but only up to this distance x1, because after x1 there is no electric field. Here the electric field is 0. Here we have some electric field. So only till here it will accelerate or deviate along y direction. After that it will just follow the same straight path, no more parabolic path. I hope that is clear. Just to recall once again, so when there is no electric field, electrons are coming out of the source, hitting this screen. Now for the distance x1 I am applying voltage, that is electric field. So using this QE relation, that means because the electron has some charge, it will experience force in y direction, and its path will, initially it was going in this direction, now we are applying force in this direction, so it will take a parabolic path like this, continuously deviating towards y direction. And after this there is no electric field. After this point, after this part there is no electric field, so its direction will remain the same and the velocity will remain the same, and it will go in this direction. This is what's the setup we have made. Okay. So initially when it just entered the electric field area, its velocity in y direction was 0 because it was initially moving in x direction. So Vx was there, but Vy was 0 before it, just before it entered the electric field area, when no electric field was there. When it enters the electric field region, then the force on it will be given by Q times E, and this I think better we should call A, which is the acceleration. This will be the acceleration due to the force of electric field. So the acceleration will be QE times M. So this is the acceleration it will experience when it will pass through this electric field region. Now what will be its displacement in y direction by the time it reaches the end of this electric field region? Electric field region is up to x1 length. So at the end of x1, what will be its y displacement? X displacement is x1, but it is also displacing in y direction. So what is that value? So now recalling equations of motion, one more slide. Yeah, so we had equation of motion, if you recollect, is v is equal to u plus at. That if we know initial velocity of a body and we know its acceleration, then after time t we can tell its final velocity. Second equation of motion is s is equal to ut plus half at square. That means if we know the initial velocity of the body and its acceleration, then after time t, what is the distance that body has covered, we can tell that. Okay. Third equation of motion says v square minus u square is equal to 2as. That is, if I know initial velocity, I know the distance it has traveled, and I know the acceleration. So you see here I don't know the time, but if I know acceleration and I know the distance it has covered, I know initial velocity, then I can tell what is the final velocity. So these are three equations of motion. So here, as we want to find out what is the displacement of this electron in y direction, that means I want to find out the displacement. I know initial velocity, which is 0, because in y direction initially the electron was not moving, right? So in y direction its velocity was 0. So I know initial velocity. Time t, after time t I want to find out what is its distance it has moved in y direction. So I'll use this equation. So distance it has covered, which is y1, initial velocity is 0, so this part will become 0, half acceleration from this equation we can find out, right? This was the force due to electric field on the electron, and force is mass times acceleration, so acceleration becomes qe over m. So acceleration I know now, which is qe by m, and the displacement, sorry, this equation we were using, and the time. Now time, how we'll find out? So velocity is distance upon time. So time is distance upon velocity. Now the distance is, we are talking about the distance traveled in, we are talking about distance it has traveled in that particular time. It has traveled x1 distance, okay, with velocity of vx, which we said is non-zero because it was moving in that direction. So the time will be x1 divided by vx, this will be t. So when we will substitute here, we will get y1 is equal to qe by 2m plus, sorry, q, there is 2m, yeah, t square means x1 by vx square, x1 by vx whole square. So this is what we get here. Now velocity, this is the displacement in y direction. Now velocity in y direction, for that we will use this first equation of motion. We want to find out in time t what is the final velocity of electron in y direction. So using second equation of motion, velocity of electron in y direction will be u plus at. Now initially in y direction the velocity was 0, so this is 0, acceleration we know and time we know. So acceleration is how much? Acceleration in y direction qe by m multiplied by time. Time is this x1 by vx, sorry, x1 by vx. So using these two equations of motion, we found out the displacement of particle when it just comes out of this electric field region, then its displacement in y direction is this, and its velocity in y direction is this. Okay. Now, so time taken by charge, as I said, t1 is x1 by vx and t2 is, so till here the time taken to travel was x1 by vx, and after this the time taken will be x2 by vx. Here electric field is different, so the velocity will be different with, and this distance traveled after that is different, so that is given by t2, which is x2 by vx. Okay, so now what happens when we from out of this vy, we let's come here. Yeah, so when we from here we rearrange q by m and put the values using these two equations. We put the values to get the these things, q by m. Finally you will be able to get this equation, and this I said this is specific charge per unit mass. In this you see, and we can see this was part of Lorentz force. You know, force is QE plus V cross B, right? So what happens is, in this experiment we know y2, okay, that the, so what is y1? Y1 was this initial distance in y direction that the electron traveled when it was influenced by electric field. But after that, when there is no electric field, it's going in linear direction, then how much distance it has covered we'll get to know when it will hit the screen. And because it's a fluorescent screen, we'll see some spot here, some spark here, so we'll be able to measure y2. Okay, now y2 we know this d is actually that electric field is v by d. So voltage what we have applied we know, the distance between the two plates we know, x1, x2, v, all this thing we know, but vx, velocity in x direction, we don't know. So for that what we have to do, we will apply, after all this is done, to understand what is the value of vx, we'll apply magnetic field in z direction. So this is x direction, this was y direction. So out of this plane, perpendicular to this plane, out and directed towards outside, is z direction. So when we apply magnetic field in this direction, we know the force due to magnetic field is v cross b. So if electron was going in this direction and magnetic field is outside, then it will start moving in y direction. Because of electric field it was going in y direction, I will apply magnetic field in such a way that it will be in opposite direction. It will be in y but in opposite direction, so that the electron motion stops and the electron reaches at the center, hits the screen at the center. So when I'll apply the magnetic field such that the electron that was hitting here at some y2 distance will come to the center. And for that magnetic field value, so this is the force due to magnetic field q v cross b, which when will become equal to the force due to electric field, the displacement in y2 will become 0, right? And when it will become 0, that means this vx we will be able to find out, which will be e by bz, or the value of e, which is v by d. So this is the, so using magnetic field we will be able to find out the velocity of electron in the x-axis. That's why we needed it. Otherwise, to find out specific charge, we needed all these things, only the vx velocity was unknown. So to find out that, we will apply magnetic field in such a way that the displacement becomes 0. Then we will be able to find these things, and q by m will become this. This is in general, we have written y, which was y2. So for generalization, we are just saying that displacement in y direction, velocity, and this k is a constant that we get from instrument, and b is the magnetic field we are applying, and then we will get specific charge, means coulomb per kg. So this was the theory behind this experiment, and yeah, so this was about this. And for the experiment detail, you can watch the video where the professor is demonstrating and explaining the experiment, how to actually do it with the instruments. Next experiment that was discussed was Frank-Hertz experiment. So this experiment tells us about the, like we were talking about atom, right? That at the center there is nucleus which is positively charged because of protons. Then we have discrete energy levels in which electron resides. So to confirm this thing in a way, so as Niels Bohr in 1913 he proposed model of atomic structure where discrete energy levels for accommodation of electrons exist. He said that it's not like earlier, because it was thought that at the center there is positive charge and electron is revolving around it like a spiral. But then the problem was, if it's revolving around like a spiral, then at the end it will fall into this positive energy, a positive charge, and because of that the matter will not be stable, it will become unstable. So then Niels Bohr said that it's not a spiral motion around the proton or the positive charge, the electrons are revolving in discrete energy levels. This is what Niels Bohr said. Now, how to verify that something like this actually is existing and there is some discrete energy gap between these levels and it's not continuous, as we were talking about earlier also for photoelectric effect, that the energy requirement is discrete. So for this was, he just postulated, Bohr just postulated this thing in 1913. In 1914, two scientists, Frank and Hertz, that's why it's called Frank-Hertz experiment, they performed experiment to demonstrate this quantum nature or discreteness of energy level in an atom. So what they did, they took a tube. So again, they filled it with some noble gas. Means noble atom or noble gas means all the atoms of that gas have closed shell configuration. They all have closed shell configuration. Means if all the whatever is, we know, right, 1s2, 2s2, so all the 1s2, 2s2, 2p6, 3s2, like that, that means all the electrons on those shells are completely filled. So they are non-reactive, that's why they are called noble gas. So they use this, then they send some electrons, accelerated electrons go through them and they are collected here at anode and we get some current. This is the usual thing. So if the more the number of electrons we are sending, the more is the electric current, and we just see this. But then what is happening when we accelerate these electrons by supplying some electric field, then at particular energy level, okay, this is energy and this is current. So we are increasing the energy by applying more potential. Electrons acceleration is more and more current we are getting, electric current. But at some particular energy, suddenly the current decreases, and then again it starts increasing, and then suddenly it dips down. This kind of observation was observed by them, these two scientists. Then they tried to understand what is happening here. And by understanding this, we understood that yes, actually, what Niels Bohr postulated, that the energy levels in atom are discrete at discrete distance, that is true. So what is happening here is, so before this G is a mesh, electrons are ejecting from here, but so that they go in this path, we are giving this this mesh or grid some positive potential, so that electrons will be accelerated towards this direction. Whatever electrons are coming out, they get accelerated in this direction. That's why we are applying some positive potential. See, this is the positive potential we are applying to this grid. So the electrons are ejected in this direction. After that, at A, we are applying negative potential, so that only the electrons whose energy is more than this, they will only reach here. This is very important significance here actually. So the observation what we are seeing, let's see further. So again, here the electron is coming out, here we are giving positive potential, at the collecting plate we are giving negative direction. And if we have, so this Frank-Hertz experiment that was conducted in 1914, It demonstrates existence of excited states in mercury atoms. It confirms the prediction of quantum theory that electrons occupy only discrete quantized energy states. This experiment supports Niels Bohr's model of atom. For this great invention, they have been awarded Nobel Prize. This was very important because as the quantum physics progressed, the field of quantum physics, many scientists started giving different theories, and Niels Bohr hypothesis was confirmed. So whenever anybody gives hypothesis, we always check if that is able to explain what we are observing experimentally in the lab. And when we are able to that theory hypothesis is able to explain the observation, then only we consider that that hypothesis is not a only. That's why initially we call it hypothesis, because we are just imagining, we are thinking, but it gets proven only when it's able to explain the experimental observation. So because they did this work, that's why they were awarded Nobel Prize for this. So this experiments consist of a tube which has a low pressure gas Hg fitted with 3 electrodes, cathode for electron emission, a mesh grid which has positive potential so that it will accelerate the electrons, and then a collecting plate. This. So what we observed with when the tube was filled with mercury gas, when the accelerating voltage, so when we increase the voltage of this plate, the electrons that are coming, they get accelerated. So more is the potential, positive potential here, higher will be their acceleration. Okay. So when the accelerating voltage reaches this 4.9 electron volt value, so we are increasing the positive potential of the mesh, and after a particular value of 4.9, okay, the current drops suddenly. But why? When we are accelerating and this plate is collecting plate is negative, that means electrons energy, when we are accelerating more and more, its energy is more than this negative potential in the collecting plate, so they should be able to go and get collected. So when we are increasing, when we are accelerating them more and more, we should get more electric current, but instead we saw it is increasing, but at some particular value, discrete 4.9 electron volt, this current suddenly drops down. Okay, this drop is due to inelastic collision between the accelerated electrons and electrons in the mercury atom. So initially, as I said, these are Nobel gas. The electrons in them and this are not Nobel gas, but there are some atoms. Okay, this so earlier the electrons are elastically colliding. So electrons were elastically colliding. Electrons were elastically colliding with the mercury atoms. That means even if they were hitting the mercury atoms, there was no interaction or nothing was happening to mercury atoms, and thus the electrons were just passing through it. That's why we are calling it elastically, because elastic collision, because there was no energy change happening here. Electrons with whatever energy were coming due to acceleration, they were hitting the mercury atoms, but there was no exchange happening between mercury atoms and accelerated electrons, and what the electron was just passing and reaching the collecting plate. But when the accelerated when we were accelerating and the voltage reaches this 4.9 electron volt energy, then what was happening, this electrons, the current that we were collecting, it suddenly, we was observing that it drops. Now why it drops? Because till now the electron and mercury atoms collision or the interaction that was happening, it was elastic. Now suddenly it becomes inelastic, means there is some energy sharing happening between them. Okay, so that's why we are calling it inelastic collision. This drop is due to inelastic collision between accelerated electrons and electrons in the mercury atoms. The sudden onset suggests that the mercury electrons cannot accept energy until it reaches the threshold. So why this drop is happening? Because the electron now collides inelastically with the electrons in mercury atom. So it's giving its energy, or the mercury atom is receiving that energy, and its electron is going to higher energy level. So this energy, only because the first excitation energy value in mercury atom is 4.9 electron volt. So like proton first 1s 2s, so the energy requirement for electron to go from 1s to 2s say is 4.9 electron volt. So when the energy of electron hitting it is equal to this value, then only it will accept it and go to 2s. If it's less than it, or if it more than it also, it will not go to high energy level. Whereas if you recollect in photoelectric effect, we were seeing it had only to eject from the surface. So whatever was the work function required, after that everything, if the incident energy has more energy than work function, electron was taking it, coming out, and everything was becoming its kinetic energy. But here it has to go from this energy level to another energy level. So its energy requirement is only this. If it's less than s, it won't go. If it little bit more than this, then also it will not accept. So only when the photon of photon or electron of that particular energy is coming and hitting it, it will go on the second energy level, and thus the electron that was going, its energy will decrease, and that's why it won't be able to reach the collecting plate. Because I told there was that's why I said it's important why we are applying negative potential to collecting plate. If we are not applying negative potential, then in case if it's positive, then all the electrons will reach there. But since I am applying some negative potential here, electron will get repelled if it doesn't have sufficient energy to reach to the collecting plate. So when this particular electron at 4.9 electron volt loses its energy to the mercury atom, then now its energy is not sufficient to overcome this negative potential and reach the collecting plate. Thus I will see a drop in the electric current. And the same thing will happen when the accelerating voltage reaches double of it, and same we will observe when the accelerating voltage triple of it. So this is what was observed. The sudden onset suggests that mercury electrons cannot accept energy until it reaches the threshold to elevate them to an excited state. Collected current drops at multiples of 4.9. As I said, double of it, triple of it. Double of it is 9.8 volt. 9.8 electron volt or 9.8 volt. Each electron volt gets sufficient energy to participate in two inelastic collision. So it will hit one atom and then it will hit another atom, because it has sufficient energy to excite another atom also. They excite two mercury atoms. So one electron will be, if one electron is accelerated to 9.8 electron volt, now it will give energy of 4.9 electron volt to one mercury atom and remaining 4.9 to another mercury atom. So it will be able to excite two inelastic collisions. They excite two mercury atoms and no energy will be left. So again at this point it won't be able to reach the collecting plate, and we'll see dip in current value. Okay. So this process will repeat for each interval of 4.9 electron volt. This will happen. Yeah, so using this experiment we can change the gas that we are using, and depending on what is the excitation energy requirement of that particular material or gas, we'll see this kind of same graph at different. For it was 4.9 electron volt. For another kind of material it will be something else, but the dips will be happening at multiples of that. This was very important experiment as we discussed, because it showed that the energy level is discrete, and if the energy of electrons hitting the atoms is not the same as the difference of energy levels, then they will not accept that, and the collision will be elastic and the electrons will just pass. This is Frank Hertz experiment, and we discussed the theory behind it. For experiment, please watch the lecture where the professor is demonstrating the experiment, and you can understand it from there, the experiment part. Next experiment is Rydberg constant experiment. So just let me save these things continuously, it's better. Yeah, and just to confirm, everything is going fine. Yeah. Okay. Okay. So this is Rydberg constant experiment. So here we study the hydrogen spectra and determine Rydberg constant. So in 1885, John Balmer discovered this formula to calculate wavelength of hydrogen spectra. In hydrogen spectra, like lights, electrons go to excited level. When it comes back, we get some emission, and they are of different color. So how to find out what is the wavelength that we get using this empirical formula given by Rydberg, which is 1 over lambda is equal to this Rydberg constant and 1 over m square minus 1 over n square, where m is the lower value, n is the higher value. When means when electron comes from higher level to lower energy level, when it comes down, it emits light. The because this is higher energy, this is lower energy, so the electron is coming to lower energy, so the excess energy is given out as light, as photon. Okay, so how to find out what is the energy of that photon or the wavelength corresponding to that light? For that purpose, Rydberg had given this formula. And for hydrogen atom, when the higher energy level to when the electrons are coming from higher energy level to the lower energy level is 1. Higher energy level can be anything, 2, 3, 4, 5, but from there when they come to m is equal to 1, then the light emitted, we call them Lyman series. And when from higher energy level to m is equal to 2 they come, then we call it Balmer. And similarly, Lyman, Balmer, then comes Paschen, then comes Brackett. These are line series, and then comes Fun series. So when from any higher energy level, when the lower energy level is 1, it's called Lyman. When lower energy level is 2, it's called Balmer. When lower energy level is 3, it's Paschen. When it's 4, it's Brackett. And when it's 5, it's Fun series. Okay, so this was what we understand by hydrogen spectra. Okay, I think so. This is about the theory, and for experiment, yeah, please see the lecture videos, because we'll focus now more on numericals. So let's start discussing. Light from an unknown source is passed through a, let's start doing these numericals. So first question is, light from an unknown source is passed through a Nicol prism. Just a minute, just wait. Okay, so let's start discussing the questions. So light from an unknown source is passed through a Nicol prism. So you know Nicol prism is something like this. One part of the calcite or any such birefringent material, and we paste another half using Canada balsam cement. So this is what makes the Nicol prism, and then we can use it as polarizer or analyzer, okay, which shows, okay, so the question is light from an unknown source, we don't know the source, it is an unknown source, it is passed through a Nicol prism which shows no variation in intensity of light. Usually we use it as polarizer, I said, and this unknown source, when it's passing through this Nicol prism, and we are seeing no variation in intensity of light. That means if that means the source is what type of polarized light. So what happens usually whenever any light passes through it, it does some polarization to it. But if the light that is passing, we are seeing no change in intensity of light, that means that this unknown source of light is circularly polarized. Why? Because a circularly polarized light shows no change in intensity when we are seeing from the plane perpendicular to the direction of wave propagation. So the circularly polarized light is its electric field vector changes like this, right? Changes like this. That's why we see circular motion. So when I see from the front, what I see is the direction of wave propagation. I'll see through Nicol prism no changes. It differs from unpolarized light in the mode of vibration. How? In unpolarized light, the electric field is in all possible directions, the electric field vector is changing. Whereas for circularly polarized light, this is unpolarized light. Whereas for circularly polarized light, the wave vector is going in like this, and then it's moving like out of plane right now. So in this case only the Nicol prism is not able to do anything, and we will get what we were like as it is. The intensity will remain as it is. So that means this unknown source must be a circularly polarized light. Okay, next question is, light from an unknown source is passed through a Nicol prism again, which shows two complete extinction in full rotation of Nicol prism. So this we had seen Nicol prism when we are using as polarizer and analyzer. Okay, so some light is passing, it gets plane polarized, then we are using analyzer. So at how we analyze, if polarizer and analyzer, they are at their optic axis is same, I mean if its optic axis is like this and analyzer also is kept like this, then whatever is coming out of here will pass here and we'll detect it. But if I change it, the optics axis of this analyzer respect to polarizer by some angle phi, okay, then we know the intensity outside will be initial intensity and cos square phi. This was Malus law, right? So when we change this phi from 0 degree to 360 degree full rotation, so depending on what kind of polarized light was coming to this analyzer, when we'll rotate it to 0 to 360 degree, we'll see many times the intensity going maximum, minimum, or completely zero. Now that depends what kind of light was coming. Okay, so what is this question is, light from an unknown source is passed through a Nicol prism which shows two complete extinction. Means when we in full rotation of Nicol prism, when we are rotating this Nicol prism with respect to polarizer by full rotation, two times the intensity goes to zero. That means I naught cos square phi. I naught was not zero because some light was coming, but we know cos phi, it becomes zero when phi is 90 degree and 270 degree. At these two angles cos phi becomes 0. Okay, and the question is saying that two times the intensity became 0. That means at these two values the intensity became 0. So what this means is that the light from the source is plane polarized, because as it's saying, if the intensity vanishes twice during full rotation, that means it's a plane polarized light, because as I showed, intensity of transmitted light through Nicol prism is given by Malus law, I naught cos square phi or cos square theta, where I is the intensity of transmitted E ray and I naught is the maximum intensity. Now theta is the angle made by plane of variation with the principal section of the prism. When theta is 90 degree, phi is 90 degree and 270 degree, intensity of transmitted light will become 0. So electric field vector was plane polarized, means it was only vibrating in one particular plane. So when my angle, analyzer's angle becomes 90 degree with respect to this, then cos phi will be 0 and I'll see no light outside. Same way, then I'll change the polarizer's angle, this 90 degree, I got nothing, and I'll change it here, I'll get something, then I'll change here, I'll get maximum intensity, then I'll change here, I'll get something, then I'll change this 270 degree, then again there will be no light coming out. That means it's a plane polarized light that is coming to the Nicol prism. So D is the correct option. Just try to understand what's happening and the things that we had discussed in previous class also, mostly it's related to that. Now third question is, if light from an unknown source is passed through a Nicol prism which shows variation in intensity from maximum to minimum. So again, unknown source, we are passing it through a Nicol prism, but what is happening here is the intensity is going from maximum to minimum twice in full rotation of the Nicol prism. Earlier case, we were seeing the intensity was going to extinction, means intensity was becoming 0. But here we see intensity is going maximum and then it's going to minimum. But it's not becoming 0 completely. It's not. It's just becoming maximum and minimum. Okay. Now this thing is happening. That means what kind of light source it was. So since the intensity is not going to 0, that means it's not plane polarized. Okay. And it's not remaining same, because for circularly polarized we know the intensity will remain same because the electric field vector is changing direction. That means here also it's not circularly polarized light. It's not unpolarized. Unpolarized light, of course not, it's passing through Nicol prism. Okay. It's going to maximum and minimum, means it's elliptically polarized. Because what is the difference between circularly polarized and elliptically polarized is that circularly polarized, the electric field vector is changing direction but its magnitude is same. But in elliptically polarized, if the light is moving out of the plane, in both the cases, the electric field vector will look like this, variation will look like this. And if it's elliptically polarized light, the light is moving out of the plane, then the electric field variation will look like this. The electric field vector's magnitude will also change. Say like here it was smallest, here it becomes maximum, then again it becomes smallest, and again it's changing direction also and magnitude also. So when this happens, what we'll see outside, if it would be circular, we'll see no change. But since it's elliptical, what we'll see when we rotate 2 times, we'll see maximum and minimum. That means it's elliptically polarized light. Okay. So this is the difference when this different kind of polarized lights pass through Nicol prism. Okay. Next question is, light from an unknown source is passed through a lambda by 4 plate. This is lambda by 4 plate, means lambda by 4 plate means it's quarter wave plate. Okay, this is a quarter wave plate. Light from unknown source is passed through quarter wave plate first and then through a Nicol prism. That means this Nicol prism is acting here as like an analyzer, which shows 2 complete extinctions. Again, 2 times intensity is becoming 0 in full rotation of the Nicol prism or the analyzer. The light from the source is. So this unknown source is giving some light. That light is passing through this quarter wave plate, and then when we are using this analyzer to analyze this and we are doing full rotation, so 2 times the intensity is going 0. That means what we are getting here is a plane polarized light, because we discussed plane polarized light has electric field vector moving in electric field component moving or varying in one direction only, and thus 2 times cos square phi becomes 0 in at 90 degree and 270 degree. So before it, what it was? After quarter wave plate is becoming plane polarized. Before it was what? So the answer will be, before it was circularly polarized light. How we know? Let's see. Circularly polarized light is made up of two simple harmonic disturbance of equal amplitude, and their phase difference is pi by 2. Their phase difference is pi by 2. Okay, that's how we get circularly polarized light. If a quarter wave plate is introduced, then additional phase difference of pi by 2 comes. Wavelength difference is lambda by 4. Phase difference is pi by 2, because you know phase is given by 2 pi by lambda times path difference. So if path difference is lambda by 4, that's why we are calling it quarter wave plate, and phase difference will be pi by 2 is introduced, making the total phase difference of, so we can, as I said, we can understand circularly polarized light as superposition of two linearly polarized like this, which are out of phase by pi by 2. When additional phase of pi by 2 is introduced to them, so the total phase difference will become either 0 or pi. Because of this, there will be retardation or advancement in these two components. In either case, the emergent light is plane polarized, as I said, and that's why we are seeing 2 times this going extinct. So the initial light was circularly polarized. Okay. Question number 5. The refractive indices for O ray and E ray are 1.65 and 1.40 respectively. Then the thickness of quarter wave plate for light of wavelength 600 nanometer is what? What is the thickness of the quarter wave plate? This we had discussed when we were discussing quarter wave plate, how we make it and how O ray and E ray behave in it, and depending on the thickness, what is the refractive index. So to find out the thickness of this quarter wave plate, if you recall, we had this formula, wavelength of the light used, and since it's a quarter wave plate, lambda by 4, and the refractive index of O ray and refractive index of E ray. This determines what should be the thickness of quarter wave plate. So here we know lambda is 600 nanometer. For refractive index is 1.65 for ordinary ray. For E ray it's 1.40. And we will do the maths. Let me use the calculator. It's okay. 600 times 9, 4 times 1.65 minus 1.4. 1.4 would be 0.25. That means 600, because this will be 1, this will be 600 times 10 to the power minus 9 meters, the thickness. Answers are in micrometers, so we will convert it into micrometer. 1 meter is 10 to the power 6 micrometer, right? That means this will be 10 to the power 6 micrometer. So it will be 600 times 10 to the power minus 3 micrometer. Removing this, it will become 0.6 micrometers. So A is the correct answer. So this should be the thickness of quarter wave plate for this wavelength when O ray and E rays refractive indices are these. Next question, question number 6. A beam of natural light of intensity, natural light, maybe I think we are talking about unpolarized light. A beam of natural light of intensity I is passed through a Nicol prism. The intensity of beam emerging from Nicol. We are talking about natural light. Okay, that means they are superposition of two incoherent plane polarized waves at right angles. If I naught is the intensity of each component, then the total component of this natural light will be I naught plus 2. This is the superposition formula actually when we have two components, and cos, this is the phase difference between these two components. For incoherent sources, the phase difference is varying randomly, okay, with time, and the average, if we take for this cos delta, the average will come out to be 0. Since this is 0, means total will be I will be 2 I naught. That means I naught intensity will be half. Okay, so the intensity of light after emerging from first Nicol prism will be I by 2. So I by 2 is the correct answer. Now, 7th question. Calculate the thickness of a quarter wave plate of quartz for sodium light of wavelength 5896 angstrom. The refractive indices of quartz for E ray and O ray are this. We have to find out the thickness of this quarter wave plate. So thickness will be given by again lambda by 4 and the difference of refractive indices. So refractive index is more for E ray. So we will take this the refractive index of E ray minus refractive index of O ray. So it will be 5896 angstrom, means this in meters, then 4 and 1.5533 minus 1.5442. When we'll calculate this, we'll get 1.5533 minus 1.5442, and this 5896 divided by 4, this difference will be 0.0091, and this 5896 divided by 4 will be 1474 multiplied by 10 to the power minus 10. It will be divided by 0.0091. This becomes 161,978.021978. If I write everything that my calculator gave, we are not supposed to. We should restrict it to some 3-4 decimal digit. And 10 to the power minus 10 meters it is. Answers are in micrometers, so I have to change this in micrometer as well. And again, 1 meter is 10 to the power 6 micrometers. So this will be the same value, 10 to the power minus 10 plus 6 micrometer. That means 6 minus 10 is 10 to the power minus 4. Minus 4, that means minus 3, minus 2, minus 1. That means 16.1978 micrometer. If I have to round it off to first decimal digit, then it will be 16.2 micrometer. So the correct answer is 16.2 micrometer. Next question, question number 8. So this is on the specific rotation, based on this optically active materials. They change the plane of polarization, the angle of plane of polarized light, right, when it passes through them. This question is based on that. So there is a tube 20 centimeter long. There is a tube 20 centimeter long, filled with solution 15 gram of sugar dissolved in 100 cc of water. It is placed in the path of plane polarized light. If the plane of polarization is rotated through 20 degree, find the specific rotation of the solution. We have to find out specific rotation of the solution. So if you remember, the angle of rotation of plane of polarization, the specific rotation is given by this. The specific rotation is okay. So the angle of rotation of the incident plane polarized light depends on specific rotation of the material of the solution, multiplied by the length through which the solution is passing. Say if the light is coming from here, that means it's passing through this 20 centimeter, or if it's coming from here, then that. Here they have told us 20 centimeter, means I think the light is coming and it's traveling through this 20 centimeter column. After that, the concentration. So how much the plane of polarization of incident light will be rotated, that depends on specific rotation of the solution, length of the column through which the light is traveling, and the concentration of the solution. Okay, so the specific rotation value will be given by theta divided by length and concentration of the solution. So the angle by which the plane of polarization is rotating is 20 degree. The length of column is 20 centimeter. Yeah. Wait. It's 20 centimeter. Centimeter. So 20 centimeter means how much, because we define this in decimeter. So 20 centimeter means 1 centimeter is 10 to the power minus 1 decimeter. So this will be 2 decimeter. 20 centimeter means 2 decimeter. So I'll put it in decimeter. Then what is the concentration? Is 15 gram per 100 cc. 15 by 100. When we will calculate this thing, this will be 10 100 divided by 15. This will be 1000 divided by 15, which will be 66.67 decimeter gram per cc. 66.67 degree decimeter gram per cc. So the correct answer is answer B. Next question is again on quarter wave plate. So we have to calculate the thickness of a quarter wave plate for sodium light, whose wavelength is this. Refractive index for E ray, refractive index for O ray is given. Yeah, so thickness again will be lambda divided by, this is for half wave plate. Okay, this is for half wave plate, so it will, the thickness will be this. For E ray, okay, E ray minus refractive index for O ray. So this will be 5893 angstrom, that means 10 to the power minus 10 meters. And then 2 times refractive index of E ray is 1.5533 minus 1.5442. When we calculate this, we'll get 5893 divided by 2, which is 2946.5 times 10 to the power minus 10 meters divided by 1.5533 minus 1.5442 to 0.0091. If I convert it into micrometer, because the answers are in micrometer, that means I'll have to multiply it with 10 to the power 6. Then it will be, let's see what this will give me, 2946.5 divided by 0.0091, okay, 323,791.208, and these values, 6 minus 10 is minus 4, 10 to the power minus 4 micrometer. This will be, it means 32.38 micrometer. 32 point, then this is the closest answer, 32.3 will be the correct answer here. Okay, next question, 10th question. So 120 gram of impure sugar is dissolved in water and the solution is made up to 800 cc. A column of length 20 centimeter containing this solution, so the length column is 20 centimeter, and in decimeter it will be 2 decimeter. So 120 gram of impure sugar is dissolved in water and the solution is made up to 800 centimeter cube. A column of length 20 centimeter containing this solution produces optical rotation of 15 degree. Optical rotation of 15 degree is produced using this sugar solution which has impure sugar. If the specific rotation of sugar is 60 degree per this decimeter gram per centimeter cube, find the percentage of purity of sugar. So specific rotation value is also given, 60 degree decimeter, 60 degree per decimeter gram per cc. Okay. Then we know theta is S times L times S. We know theta, we know S, we know L. Then we can find out the concentration. That will be theta over S times L. From concentration we will see how much of purity pure sugar is there in this solution. So for this the theta is 15 degree, specific rotation is the 60 degree and length is 2 decimeter. This means 1 by 8, the concentration is 1 by 8 gram per cc, because concentration we tell in gram per cc. Now what is happening here is, let me take one slide. So this is the concentration. Concentration comes out to be 1.8 gram per cc. That means 1 gram of pure sugar, because the optically active material is sugar only, so whatever is the impurity in it, that is not influencing the rotation of plain polarized light. That's why what matters, the concentration from this formula is the concentration we are getting is of, this concentration is of pure sugar, because only sugar has the optical property, other material mixed in it does not have. So the concentration we are getting here is of this pure sugar. Okay, so what this means is 1 gram of pure sugar is there in 8 cc solution. That means 8 cc solution, if I'll write it reverse, 8 cc solution has 1 gram of pure sugar. That means 800 cc solution. So see again, 8 cc solution has 1 gram of pure sugar. That means 1 cc solution has 1 by 8 gram of pure sugar. That means 800 cc solution will have 1 by 8 times 800 gram of pure sugar. Why we want 800? Because in the question it's given that the sugar, impure sugar is dissolved and the solution is made up to 800 cc, and we want to find out how much pure percentage of sugar is there in this 800 cc. So from this concentration value we understood 1 gram of pure sugar is there in 8 cc. That means in 800 cc 1 by 8 times 800 gram of pure sugar is there. How much is this? 100 gram. That means this 800 cc solution that we had made, it has 800 gram of pure sugar in it, and we had used 120 gram in the question. As you can see, we had used 120 gram of sugar which has some impurity also to make 800 cc solution. But we know the optically active material in this solution is sugar, the remaining thing is not optically active. So the concentration we are getting from this formula is only for the pure sugar part. So that means this 800 cc has pure sugar only 100 gram. That means this 120 gram minus this 100 gram, this was impure sugar that we used, and from concentration we got 100 gram pure sugar is there in 800 cc. That means that 20 gram is impurity. Now we need to find out percentage of purity of sugar. So for percentage of purity of sugar, in 120 gram of sugar, 100 gram pure sugar was there. Right? In 120 gram impure sugar, 100 gram of pure sugar was there. That means in 1 gram impure sugar, 100 over 120 gram of pure sugar was there. That means in 100, in percentage it means 100 divided by 120 times 100. Okay, so this will be 100 divided by 120 multiplied by 100 because we want percentage. So this will be 100 divided by 12 multiplied by 10, just 83.33%. Okay, so this is the purity of the pure sugar here. 83.3% is the purity of sugar in the solution. Okay, next question, which is also the last question. The electric field component of a plane electromagnetic waves. This is a plane polarized light. Its x component is this and y component is this. Find the state of polarization of the wave when it propagates along z-axis and when the phase difference phi is 0. Okay, so what would be the state of electric field component of plane electromagnetic wave is this and this. Find the state of polarization of the wave when it propagates along z-axis. So what happens is, we'll set some boundary condition that it's propagating along z-axis. Okay, and now at z is equal to 0, just when it started, before it just started propagating, we put this boundary condition, that is z is equal to 0 and phi is equal to 0 anyway is given. So what will happen to Ex component? If we substitute z is equal to 0 and phi is equal to 0 here, Ex will become E naught cos omega t. This will become 0 for, I should not write here, and this will become 0 and phi also will become 0. So this is what we will get at this boundary condition. What will happen to Ey? Ey will become, with this boundary condition, Ey will become 2 E naught sine, now z is 0, that means sine omega t. At this boundary condition, Ex and Ey component will become this. Now from this we can write Ex over E naught is cos omega t. From this we can write Ey over E naught or 2 E naught is sine omega t, right? Just rearranging these two equations, we will get this. Now if I take square of these two and add them, what will I get? Ex over E naught, if I take square of these and add them, and now this Ey by 2 E naught, if I take square of this and add them, I'll get cos square omega t plus sine square omega t. We know from trigonometry, cos square theta plus sine square theta is 1. So if you see this, okay, this is like equation of ellipse. If you recall, ellipse is like this. This is major axis, this is minor axis. Okay, an equation is given by if this is x-axis and this is y-axis, then equation becomes x square by a square, this is a, plus y square by b square is equal to 1. This is half of major axis, this is half of minor axis. Okay, this is the equation of ellipse. Same way, if you see for this ex, ey value, let me again take one more slide. If you see the ex, ey, this has this half of major axis, half of minor axis thing. This is ex, this is ey. Okay, then this is e naught, and this is 2 e naught. Okay, then e naught should be here. So it's something like this. That means the final thing is, it is like also with this, I'm just telling directly, but we can also find this out. So in this equation which is ex square divided by e naught square plus ey square divided by 2 e naught whole square is equal to 1. In this equation we have cos square omega t plus sine square omega t. Even if you don't do this, what happens is, we'll take at t is equal to 0. At t is equal to 0, when you put here, sine square will become 0, only this will remain, which is, so this will be cos square, and cos square 0 is 1. That means when this is 1, ex is 0, ey is, ex is e naught, ey is 0, and t is equal to, so when we put this is 0, that means this component I am saying is 0, and only this will remain. That means ex is e naught, then I'll take t is equal to pi by 2 omega, and then I'll get this 0, and this ey will become 2 e naught. So basically, yeah, this only tells that these two components, the resultant state of polarization we are getting is elliptically polarized light. So this is the correct answer for this. So with this, today's session finishes, and so this was about this, I think is the, yeah, this is the last week lecture for this 12-week course. So till now we were discussing about till previous week we were discussing about all the optics experiment, and now we are discussing about all these quantum physics related thing. So you guys can ask doubt. If not, then I'll stop the recording.